Namaste and welcome to my presentation. I am Abbas Maske, currently the project manager for BIRDS-3 satellite project, which also built the first satellite for Nepal. I'm just going to give you an overview of the project and also the current operational status. We have been operating the satellite for almost about a month now, so I'll give you some updates on that. If you do want to ever contact me, my email address is right down here. Please feel free to contact me anytime. Agenda for today, we'll have a look at the BIRDS-3 project. I'll give you a brief introduction. We'll look at how Nepal and Japan ended up collaborating together for NepaliSat-1. We'll look at the purpose for NepaliSat-1, what the design and operation was, the outreach that we are trying to do with the satellite, and we'll do a Q&A session at the very end. BIRDS introduction. So what is the BIRDS project? It's a shortened form for Joint Global Multinational BIRDS Satellite Project. It was very weird to say JGMNBSP, so we just put BIRDS instead of having that long name. So basic idea is to target non-spacefaring countries, which also included Nepal. And we wanted to build, test, launch, and operate satellites in 2 years. So we had BIRDS-1, BIRDS-2 before us. We are in the BIRDS-3 project, and we also have BIRDS-4 coming up next year. BIRDS-1 and BIRDS-2 had different countries involved. BIRDS-1 had Ghana and Mongolia and Bangladesh, which built their first satellites. There was a constellation of 5 satellites in total. In BIRDS-2, we had Bhutan, which built their first satellite. And in case of BIRDS-3, we have Nepal, Sri Lanka, and Japan participating. We also have 1 member from Bhutan. So our mission statement is to successfully build Sri Lanka and Nepal's first satellite. We have 8 members in the team, 1 undergraduate, 1 PhD, and the rest is master's degree students. Each person had a specific assignment, a specific subsystem to take care of. And as you can see, NepaliSat-1 was not only built by Nepalese, but we also had Japanese, Bhutanese, and Sri Lankan involved. Likewise, we also worked on Sri Lankan satellites, and we also worked on the Japanese satellite. So it was a win-win situation for all the teams. We have, as I had stated before, 3 satellites. The Japanese satellite is called Uguisu. The Sri Lankan satellite is Raavana-1, and Nepal satellite is NepaliSat-1, as you have already listened to it before. The stakeholder for Uguisu is Kyushu Institute of Technology. Raavana is Arthur C. Clarke Institute for Modern Technologies, and in case of Nepal, our stakeholder is Nepal Academy of Science and Technology. Let's have a look at the collaboration between Nepal and Japan. According to our government's plan, it was written that we would build a satellite by the end of the 14th plan, which was last year in Bikram Sambat. The idea was to use Nepalese resources, funding, and also human. And we wanted the project to finish when the plan finished as well. So we asked ourselves, what was the minimum optimum way we can complete this? Is there any project that we can actually look into and get involved in? Kyushu Institute of Technology is one of the top leading institutions for small satellite development. As you can see, we are ranked number 1 for all small satellites launches in the world. We have testing facilities for charging and discharging and have been involved with a number of institutions in Japan and also abroad. We also have a testing facility for nano satellite. We have thermal vacuum testing, small vacuum thermal vacuum testing for space environment. We also have vibration testing for rocket environment, shock to induce rocket environment as well, and anechoic chamber for testing and calibrating antennas. So far, we have tested all these satellites. Timeline for NepaliSat-1. So we gave the first presentation about birds in 11th April of 2017 in Ministry of Science and Technology. After the proposal was submitted, the pre-CRA was signed in 22nd September 2017 by Nepal Academy of Science and Technology. NAS took leadership in the project for Nepal, and that's how it's moved forward. The project started on 1st October 2017. The funding was approved on 14th November 2017, so you can see that the project actually began even before the funding was approved. Cooperative research agreement was exchanged on 17 January 2018. The government was able to pay 76.7% by April, and by September 2018, full payment was done. So this was just for the satellite development cost. We then finished building the satellite, and the press release was on February 15, 2019. The project timeline is as follows. We had a project kickoff on 4th October 2017, mission design review, which explains what kind of missions we're going to have by 28 December 2017. We had preliminary design review, which shows the BBM breadboard model, a working concept of each subsystem by 24th April 2018, and then we showed an integrated system by 1st September 2018, and finished with the flight model, which was the actual satellites that we are going to send on January 2019. Delivery was done February 18, and launch was by NG-11, a resupply mission to ISS, on April 17th. Deployment was then done on June 17, and we have firmly been operating the satellite since then. What is the purpose of NepaliSat-1? So the motivation comes from the earthquake in Nepal in 2015. So we all know what happened at the time, and what we saw was that there were two special bottlenecks. One was on communication. So if we wanted to pass information from point A to point B, it was a problem. And also, what we noticed was if we had some system that allowed us to look at landscape changes and look at where tents were, or look at how structures were being destroyed from a vantage point of view, that would have been useful, right? So we looked at two parts, and we thought, can we do something about it in our satellite? So our primary mission is to do remote sensing. Eventually, in the future, what we want to do is something what Planet Lab is doing. They're taking RGB images, and you can get a resolution of about 3 meters, 5 to 3 meters. That would be useful data. However, to reach that point, we need to show that we can take an image. So first step that we wanted to show towards making a remote sensing satellite is to build a system that can take images from space. So that was our primary mission. Second mission is to qualify a very long-range module called LDM. So this one is LoRa demonstration mission. The type is called, the communication type is called LoRa, long range. And what we want to do in the future is have all these sensor terminals around the world. And these sensor terminals could be anything. It could be water level sensors, it could be message centers, it could be temperature sensors. And these information will be then sent to the satellite, stored in that satellite, and then later downlinked on the ground station. But to do that and to reach that stage, we need to first qualify the module. So that was our secondary mission. So if we could somehow prove that this works in space, then in the future missions we can use it as a communication module. Okay? So let's have a look at the design and operation. Our operational concept is such that the launch was completely handled by Japanese Aerospace Exploration Agency, and then later on deployed from the International Space Station. So since it was deployed from International Space Station, we had no control over what orbit it would be deployed in. We already knew that it would be in 400 kilometers. The inclination is 51.6 degrees. We have a period of about 90 minutes, so 60 minutes of sunlit time, 30 minutes of eclipse time. Frequency for communication, we're using amateur band, amateur UHF, and that will be 4800 bit per second for both uplink and downlink. We have 15 ground stations spread all around the world, and most of them have already received the beacon signal. NASA is currently building the ground station in Nepal. What about the satellite? The satellite itself is a CubeSat standard. CubeSat standard is basically 100 by 100 by 100 millimeter, and it weighs about 1 kilo. And the harnessing type, what I mean by harnessing is subsystems have to be interconnected. To be able to interconnect them, we need some kind of wire. But instead of using wire, we're here using PCBs. So all the PCBs will be stacked on top of each other. Missions. So we have camera mission, as I mentioned before. The ground swath is about 700 kilometer by 350 kilometer. In nadir pointed state. The ground sampling distance is about 1.2 kilometer for 640 by 480 resolution. We also have active stabilization. So once the satellite is deployed, it starts tumbling, and we need to stabilize that first. We have a PCB magnetotorquer, which allows us to control the rotation on each axis. We also have the LoRa demonstration validation module. So we want to validate whether the module will work or not in space. And as I mentioned before, we want to create a communication subsystem in the future. Actually, we're already doing that with BIRDS-4. And backplane board. So as I showed before, what we're trying to do now is before it's hardwired, now we want to use software to change these routes. So that was also one of our missions, and see if that would work or not. So what kind of image are we getting? We expect to get images like these. We already have these images, but we are not allowed to publish it at the moment. We are waiting for full license of our ground station, and the inspection is going to be held on the first week of August. Then we can release all the images that we have taken. The MTQ design looks like this. So on the outside, you cannot see the traces, but from the inside, you will notice that these are all traces that allows us to then have current flowing through them and create a magnetic field which then interacts with the magnetic field of the Earth and creates a torque that allows the satellite to rotate. The LDM mission board looks like this. We have two modules. Nothing is being emitted, nothing is being received. All we are doing is transmitting information from one end to another. To avoid transmission of any RF, we have placed a 20 dB attenuator here in between. Once we validate the information coming from one module to another is correct, then we know that the module itself is working. This is the software-defined backplane board. All the PCBs are going to be on the top of these connectors, and we can then, using software, change the routes between those PCBs, and this we want to create into a commercial product in the future, so this was the first step towards that. So far, we have conducted the camera, ADCS, LDM backplane board. So basically, all the missions have been conducted. We have completed the camera mission, LoRa demonstration mission, and backplane board mission, and we are currently activating the ADCS mission. Okay. So the satellites, all of the satellites are healthy and are operational.